Welcome everyone to the deep dive. Today we're embarking on a really crucial exploration. It's something that forms the very foundation of your chemistry journey,
Right.
especially if you're preparing for board exams or, competitive examinations like NEET, JG, UPSC, SSC, and state PSCs.
Right, those are definitely on my radar.
We're talking about chemical reactions and equations, and understanding this chapter, it isn't just about scoring marks. It's really about building that core conceptual clarity you'll absolutely need throughout your scientific studies.
Exactly. I'm really looking forward to this session. From what I understand, this chapter truly underpins so much of chemistry. Mastering it feels like, a direct pathway to confidently tackling more advanced topics later on.
You've got that absolutely right. I mean, just think about our everyday lives. They're brimming with chemical changes, often without us even realizing it.
Like what, for instance?
Well, have you ever considered what truly happens when milk sours if it's left out in the summer heat? Or when an iron gate starts to rust after a few monsoons?
Oh yeah, rusting is a common one.
Or even the magic behind grapes fermenting into wine, the complex transformations as we cook our food, that intricate digestion process inside our bodies, or even just the simple, vital act of breathing.
Those are all such common occurrences, yeah. Things we often just take for granted.
Precisely. And in each of these instances, if you look closely, you'll see a really profound change. The initial substance completely transforms its nature, its identity. It becomes something entirely new.
Okay.
Now, you've already learned about physical and chemical changes in your earlier classes, right?
Yes, I remember that.
Yeah.
Physical change is reversible, chemical change isn't, usually.
Right, exactly. And the key insight here is pretty straightforward. Whenever a chemical change happens, it's a definitive sign that a chemical reaction has occurred.
So chemical change equals chemical reaction.
Got it. Our mission in this deep dive is to really understand the essence of a chemical reaction. How do we identify it? How do we represent it in the universal language of chemistry? And crucially for your exams, what are the distinct categories these reactions fall into?
Okay, sounds like a plan.
Right, let's start unpacking this essential bedrock of chemistry. So, first things first. How do we actually know a chemical reaction has taken place?
This is a fundamental question. It often comes up in both theoretical and practical exams.
Right, how do we spot one?
It's not always visible at a glance, but chemists rely on four primary indicators. Four sort of telltale observations that signal a chemical transformation is underway. Mastering these is really crucial for both practical identification and theoretical understanding.
Okay, four indicators, what are they?
The first indicator is a change in state. When reactants interact, the products formed can actually have a completely different physical state than what you started with.
Change in state, like solid, liquid, gas. Exactly. Imagine starting with, say, two liquids and suddenly you see a solid forming and settling down. That's a precipitate. Or maybe you mix things and a gas starts bubbling off.
Ah, okay.
This transformation from solid, liquid, or gas to a different state is a powerful visual cue that new substances have been created.
Makes sense. What's the second one?
The second is a change in color. This is often one of the most striking and, easily observable signs.
Like a color appearing out of nowhere.
Pretty much. A distinct color transformation, for instance. You mix two clear solutions and suddenly witness a vibrant yellow or maybe a cloudy white appearing that immediately suggests entirely new chemical entities with different optical properties have formed. It's like watching a magic trick, but, it's pure chemistry.
Okay, change in state, change in color. What's next?
Our third indicator is the evolution of a gas. This is usually identified by the rapid formation and release of gas bubbles.
Like fizzing.
Exactly like fizzing. Think about dropping an antacid tablet into water. That vigorous fizzing you see. That's a direct result of a chemical reaction producing carbon dioxide gas.
Right, I've seen that.
So the appearance of bubbles where none existed before is a really strong clue. A reaction is happening.
Okay, state, color, gas. One more.
And finally, a highly significant indicator, a change in temperature.
Ah, getting hotter or colder.
Precisely. At its core, a chemical reaction involves breaking old chemical bonds and forming new ones. These processes inherently involve energy.
Okay.
If a reaction releases heat into the surroundings, making the container feel warm or even hot, it's termed an exothermic reaction.
Exo means out, like heat going out.
You got it. Conversely, if a reaction absorbs heat from its surroundings, making the container feel cool or even cold, it's an endothermic reaction.
Endo meaning in, heat going in.
Perfect. These temperature shifts provide vital clues about the energy changes happening during the reaction.
So change in state, change in color, evolution of gas, and change in temperature. Those are the four.
Exactly. Now, to truly grasp these, let's quickly recall some foundational activities. These are often covered in your practical curriculum, and importantly, they frequently pop up in theory questions. So understanding the observations is key.
Okay, like experiments.
Yes. First, let's consider activity 1.1, the burning of a magnesium ribbon. This is a classic one.
I think I remember this one. Bright light.
That's the one. In this activity, you take a small piece of magnesium ribbon, maybe 3-4 centimeters long. First, you clean it with sandpaper. Then you hold it with tongs and ignite it using a spirit lamp or Bunsen burner. The ash that forms is collected usually on a watch glass.
Why clean it first? Does that matter?
Good question. That's a critical safety and procedural point, often asked in BIVAs. When magnesium sits in air, it forms a thin kind of unreactive layer of magnesium oxide on its surface.
Oh, like a protective coating.
Exactly. Sanding removes this layer, ensuring the fresh reactive metal underneath is exposed. This gives you a complete and, well, vigorous reaction. Safety first, though always use tongs and eye protection, and don't stare directly at the flame.
Got it. So what happens when it burns?
The key observation here is that the magnesium ribbon burns with an incredibly dazzling, bright white flame. It's very intense, and it transforms into a fine white powdery ash. This ash is magnesium oxide.
Wow, okay.
Now think about our indicators. The single observation actually demonstrates several of them.
Let's see. The state changed from solid metal ribbon to solid powder.
Right.
The color changed from silvery white metal to pure white powder.
Yep.
And the dazzling flame obviously means light and heat were released. So temperature changed too. It's exothermic.
Exactly. So that one activity shows change in state, change in color, and a temperature change. Nicely summarized.
So that activity covers three indicators at once.
Yeah.
State, color, and temperature change. Is it always so clear-cut, or are there reactions where maybe only one indicator is obvious?
That's a great question. It varies. While some reactions, like the magnesium burning, give you multiple clear indicators, others might predominantly show just one.
Like the antacid tablet.
Precisely. The fizzing of an antacid primarily demonstrates gas evolution. The key takeaway is that observing any one of these changes is sufficient evidence that a chemical reaction has occurred.
Okay, that makes sense.
Right. Let's quickly review activity 1.2. This one involves mixing lead nitrate and potassium iodide solutions. Both are usually clear, colorless solutions.
So what happens when you mix them?
Here, you simply mix the two clear solutions in, say, a test tube. The immediate observation is the formation of a white substance that is insoluble in water. It just appears instantly.
A white solid from two clear liquids.
Exactly. This insoluble solid is what we call a precipitate. Its formation is a clear indication of a chemical reaction. This type, we'll learn later, is often a double displacement reaction. We'll come back to that.
Okay, precipitate formation. Got it.
Finally, for this section, let's consider activity 1.3, the reaction of zinc granules with dilute acids.
Zinc and acid. I think I know this one too. Bubbles.
You're right on track. If you add a few zinc granules to dilute hydrochloric acid, or maybe dilute sulfuric acid in a conical flask handling the acid carefully, of course you'll immediately observe bubbles rapidly forming around the zinc granules.
That's the gas evolution indicator.
Correct. It signifies the evolution of a gas, which in this case is hydrogen gas. Furthermore, if you were to touch the flask, you'd notice it feels warm.
So temperature change as well. Exothermic again.
Exactly. So this activity clearly demonstrates both gas evolution and a temperature change, confirming a chemical reaction.
Okay, those examples really help illustrate the four indicators.
Good. So, in summary, recognizing these four key observations, a change in state, a change in color, the evolution of a gas, or a change in temperature, is your first and most fundamental step in identifying that a chemical reaction has indeed taken place. This understanding is absolutely foundational for everything else in this chapter.
Right, makes sense.
Okay, now that we know how to identify a chemical reaction by observation, the logical next step is to explore how we represent these reactions.
You mean writing them down?
Precisely. Just like mathematics uses symbols and equations, chemistry employs a concise and universally understood language. Chemical equations. They serve as a powerful shorthand to describe chemical reactions efficiently and accurately.
Okay, so how do we start?
We usually begin with what are called word equations.
Yeah.
This is the most descriptive sort of sentence-like form. Remember activity 1.1, the burning magnesium ribbon?
Yeah, the dazzling white flame one.
We could describe it in a full sentence. When magnesium ribbon is burnt in oxygen, it is converted to magnesium oxide. That's a bit long, right?
Yeah, a bit wordy.
So we can simplify this into a word equation. Magnesium plus oxygen, magnesium oxide. Much shorter, clearer.
Okay, that's simpler. What do the parts mean?
Good question. In this structure, the substances undergoing the chemical change here, magnesium and oxygen are called the reactants. They're always written on the left-hand side, LHS, of the arrow.
Reactants on the left. Okay.
The new substance formed in this case, magnesium oxide, is the product. It's always written on the right-hand side, RHS, of the arrow.
Products on the right.
The arrow itself indicates the direction of the reaction. It means yields or produces. And if you have more than one reactant or product, you separate them with a plus sign, plus. This basic format is critical.
Magnesium plus oxygen, magnesium oxide, reactants yield product.
Got it. Word equations seem quite descriptive and pretty easy to understand. Why is it so crucial then to learn to write them using chemical formulae? And what exactly does skeletal equation mean in that context?
That's an excellent point, and it leads us right to the heart of chemical representation. While word equations are descriptive, they can be cumbersome, especially for complex reactions. Plus, they lack the universal precision needed for serious chemical communication.
And for calculations, I guess.
Exactly. Especially for the quantitative analysis required in competitive exams. Imagine writing out long chemical names repeatedly. It's just not efficient. This brings us neatly to 1.1.1. Writing a chemical equation using chemical formulae.
Okay, using symbols like Mg for magnesium. Precisely. Using chemical formulae makes equations far more concise, precise, and, importantly, universally understood by scientists everywhere. For instance, our word equation, magnesium plus oxygen, magnesium oxide, becomes simply Mg plus O2 See how much shorter that is?
Yeah, much more compact.
Now, this equation, where we've used the correct chemical formulae for reactants and products, but haven't yet checked if the number of atoms of each element is the same on both sides, that is called a skeletal chemical equation.
Skeletal, like just the basic framework.
Exactly. It represents who is reacting and what is forming using the right formulae, but it might not be balanced yet. In Mg plus O2 you can see one MM on both sides, but two O atoms on the left in O2 and only one O on the right in MgO. So it's skeletal because it's unbalanced.
Ah, okay, so the skeleton needs fleshing out, kind of.
That's a good way to put it. It needs to be balanced to reflect reality. And this leads us directly to 1.1.2, balanced chemical equations and the law of conservation of mass.
Right, I remember this law from class 9s. Mass isn't created or destroyed.
Exactly. You would have studied this bedrock principle, the law of conservation of mass. It states very fundamentally that mass can neither be created nor destroyed in a chemical reaction.
Okay.
Now think about the implication for chemical equations. If mass is conserved, then the total mass of all the elements present in the products must be equal to the total mass of all the elements present in the reactants.
The total weight on both sides of the arrow must be the same.
Precisely. And what does that mean at the atomic level? It means the number of atoms of each individual element must remain the same before and after a chemical reaction. Atoms just rearrange, they don't vanish or appear out of thin air.
So you can't lose an oxygen atom or gain an iron atom during the reaction.
Absolutely not.
Yeah.
Therefore, to obey this fundamental law and represent a chemically valid reaction, every skeletal chemical equation must be balanced. An unbalanced equation fundamentally violates the law of conservation of mass.
So balancing isn't just neatness, it's a fundamental law.
It is absolutely fundamental. Let's consider a balanced example first, just to see what it looks like. Remember, activity 1.3. Zinc reacts with sulfuric acid to form zinc sulfate and hydrogen gas.
Zinc plus H2SO4 goes to ZnSO4 plus H2.
Perfect. Now let's count the atoms on each side.
Okay. Zinc, Zn, one on the left, one on the right, balanced.
Yeah.
Hydrogen, H2 on the left and H2SO4, two on the right and H2, balanced.
Right.
Sulfur, S1 on the left, one on the right, balanced.
Yep.
Oxygen, O4 on the left and H2SO4, four on the right, and ZnSO4, also balanced.
Excellent. Since all the atom counts are equal for every element on both the LHS and RHS, this equation, Zn plus H2SO4 is ZnSO4 plus H2, is already balanced.
Okay, that one was easy. But what about the skeletal ones, like Mg plus O2 EMgO?
Exactly. Many equations are not initially balanced, and balancing them is a guaranteed skill tested in all your exams. It's something you have to master. Let's tackle a crucial example together. The reaction of iron with steam to form ferric oxide, specifically iron 2 oxide and hydrogen gas.
Iron plus steam.
The skeletal equation is Fe plus H2O, FeO4 plus H2. We'll balance this using the systematic hit and trial method. It's called that because it involves making successive logical adjustments until balance is achieved.
Hit and trial. Sounds a bit random.
It can feel that way at first, but there's a strategy. Let's go step by step. Step I. A golden rule for balancing, especially helpful when you're starting or dealing with complex equations, is to first draw imaginary boxes around each chemical formula. Fe plus H2O, Fe3O4 plus H2.
Why the boxes?
This visually reinforces a critical point. You cannot change anything inside these boxes. You can't change H2O to H2O2 or Fe to F2, for example. You can only place whole number coefficients in front of the entire formula to change how many molecules you have.
Okay, don't mess with the formula themselves. Got it.
Step 2. Now, let's list the number of atoms for each element on both sides of the unbalanced equation.
Okay, Fe, left side 1, right side 3.
Right.
H, left side 3, right side of U. That one's okay for now.
Yep.
O, left side of 1, right side of 1, 4.
Good. Clearly, iron Fe and oxygen O are unbalanced.
Right.
Step 3. Now, the strategy for hit and trial. It's usually best to start balancing with the compound that contains the maximum number of atoms. Look at our equation. Fe, H2O, F3O4, H2. Which compound has the most atoms?
Fe3O4. It has 3 Fe and 4 O, so 7 atoms total.
Excellent. Now, within Fe3O4, which element has the highest number of atoms?
Oxygen with 4 atoms.
Perfect. So let's start by balancing oxygen. We have 4 oxygen atoms on the RHS in Fe3O4, but only 1 on the LHS in H2O. How can we get 4 oxygen atoms on the LHS?
You need to put a 4 in front of the H2O.
Exactly. We place a coefficient of 4 in front of the entire H2O formula. The equation now becomes Fe plus 4H2O, Fe3O4 plus H2.
So now we have 4 oxygen atoms on both sides.
Correct. And remember, we did not change H2O to H2O4 or anything like that. Just 4 molecules of H2O.
Got it.
Step by Fe. Okay, oxygen is balanced. But notice, placing that 4 in front of H2O has affected the hydrogen count on the LHS. How many hydrogen atoms do we have on the LHS now?
We're 4H2O, that's 4 times 2.8 hydrogen atoms.
All right, now look at the RHS. In H2, we still have only 2 hydrogen atoms. How do we balance the hydrogen?
We need 8 on the right too, so put a formant in front of the H2.
Perfect. Place a coefficient of formant in front of H2 on the RHS. The equation now stands as Fe plus 4H2O, a Fe3O, plus 4H2.
Okay, oxygen is balanced, hydrogen is balanced, just iron left.
Exactly. Step V. Only one element remains unbalanced. Iron. Look at the RHS in Fe3O4. How many iron atoms are there?
3. Fe,
And on the LHS in Fe, how many do we have currently?
just 1.
So how do we balance the iron?
Put a 3 in front of the Fe on the left.
You got it. Place a coefficient of 3 in front of Fe on the LHS. The equation finally becomes 3Fe plus 4H2O at A3O4 plus 4H2.
Okay, let's check everything now.
Step 6. Absolutely crucial final step. Always perform a final check. Count all atoms again for every element.
Fe, LHS 3, RHS 3, balanced.
Good.
LHS 4 by 2 equals 8. RHS 4 by 2 equals 8.
Good.
RHS at 4 by 1 and Fe3O4.
Balanced. Excellent. Since all the atom counts are equal for every element, the equation 3Fe plus 4H2O, Fe3O4 plus 4H2 is perfectly balanced. This methodical hit-and-trial approach, using the smallest possible whole number coefficients, is a vital skill for exam success.
That step-by-step breakdown is really helpful. For more complex equations, though, what's a general tip for selecting the first element to balance? That seems like the most critical initial choice, the one that can make it easier or harder.
You've highlighted the most common sticking point for students.
Absolutely.
The main strategic tip is this. Always try to begin with the compound that contains the maximum total number of atoms. It's often the most complex-looking one.
Like Fe3O4 in our example.
Exactly. Once you've identified that compound, then focus on the element within that specific compound that has the highest number of atoms. In Fe3O4, that was oxygen. Starting there often resolves a large part of the imbalance early on.
Okay, so biggest compound, then biggest atom count within it.
Right. Elements like hydrogen or oxygen, especially if they appear in multiple compounds on one side, or maybe they appear as a simple element like O2 or H2, those are usually best left for the later stages of balancing. Their coefficients often get adjusted more easily as you balance the other, more complex elements first. So remember the mantra, most atoms in a compound, then most atoms of an element within that compound. That usually sets you on the right path.
Got it. That's a useful strategy.
Now, beyond just balancing the atoms, there's one more step to make equations even more informative. Step 7 involves writing symbols of physical states and reaction conditions.
Making it more detailed.
Exactly. A balanced equation tells us what reacts, what is formed, and how many atoms or molecules are involved. But to make it truly informative, especially for practical work or understanding industrial contexts, we often add the physical states of the reactants and products, and sometimes the conditions under which the reaction occurs.
How do we show the states?
We use standard notations, usually in parentheses right after the chemical formula. We use S for solid, L for liquid, G for gas.
Solid, liquid, gas. Okay.
And there's one more very important one, AQ, for aqueous solution. This means the substance is dissolved in water. This aking notation is particularly important for competitive exams, as it helps distinguish reactions happening in solution from those involving pure liquids or solids.
Okay, AQ for dissolved in water.
Right. So let's apply this to our balanced iron-steam reaction. It becomes 3Fe plus 4H2AS plus 4H2S plus 4H2G.
Let's see. FeS means solid iron.
Correct.
H2G means water is a gas.
Precisely. This is crucial here. It means the water is in the form of steam, not liquid water. Iron reacts differently with steam than with liquid water.
Okay, that's important detail. Then F3O4 is solid ferric oxide.
Yep.
And H2G is hydrogen gas.
Perfect. While including physical states isn't always mandatory unless asked, it adds significant clarity to the reaction's description.
Okay. What about reaction conditions? Good point. Sometimes specific conditions needed for the reaction to happen, like temperature, pressure, or the presence of a catalyst, are indicated above or below the arrow in the equation.
Like needing heat or something.
Exactly. For example, in the industrial synthesis of methanol, the reaction is COG plus 2H2G CH3OHL. You might see 340 at arrow written above the arrow, signifying the high pressure required.
Wow.
Or, for photosynthesis, the overall reaction is often written with sunlight above the arrow and chlorophyll below it, highlighting the energy source and the biological catalyst needed. Including these details transforms the equation into a really comprehensive summary of the entire chemical process.
So balanced equation plus states plus conditions gives the full picture.
That's the idea. It makes the equation much more informative. Right then. Now that we've mastered the language of chemistry, how to write and balance equations, let's dive into the fascinating variety of chemical reactions themselves. Understanding these types of chemical reactions is absolutely paramount for your board exams and competitive tests.
Why is knowing the types so important?
Because questions frequently ask you to identify the reaction type, predict the products based on the type, or relate a specific type to real-world phenomena or industrial processes. It helps you categorize and understand chemical behavior.
Okay.
And remember that core idea from Class 9X. During a chemical reaction, atoms don't magically change into other elements. They don't just disappear or appear out of nowhere. Instead, chemical reactions fundamentally involve the breaking of old chemical bonds between atoms and the reactants and the formation of new chemical bonds to create the products. It's all about this atomic rearrangement, this choreography.
Breaking old bonds, making new ones. Got it.
So the first major type we'll explore is the combination reaction. As its name clearly suggests, this is a pretty straightforward process. It's where two or more substances, and these can be elements or compounds, combine or join together to form a single, more complex new product.
Two or more things making just one thing.
Exactly. Think of it like individual Lego bricks snapping together to build one larger, unified structure.
Okay, simple enough. Any examples?
A very common and industrially relevant example comes from Activity 1.4. The reaction of quicklime with water. Remember quicklime, calcium oxide, CaO.
Yeah, you mentioned it earlier.
Right. If you take a small amount of this white powder, quicklime, in a beaker and slowly add water to it, then carefully touch the outside of the beaker, you'll observe something quite significant.
Why not?
The mixture will undergo a vigorous reaction. You might see it bubble or steam a bit, and crucially, the beaker will become noticeably warm, sometimes even quite hot. This clearly indicates a substantial release of heat.
Ah, the temperature change indicator again. It's exothermic.
Exactly. The equation for this reaction is CaOS plus H2OL, KOH2AQ plus heat. Here, solid quicklime, calcium oxide, and liquid water combine to form calcium hydroxide, which dissolves in water to form an aqueous solution. Calcium hydroxide is also known as slaked lime.
CaO plus H2O makes KOH2. Two things made one.
Precisely.
Yeah.
Since two reactants, CaO and H2O, combine to form a single product, COH2, this is a classic combination reaction. And as we noted, it releases heat.
Okay. Are there other common examples?
Oh, absolutely. Think about the everyday burning of coal. Coal is mostly carbon, C. When it burns, it combines with oxygen gas, O2, from the air. What does it form?
Carbon dioxide.
CO2, exactly. CS plus O2G, CO2D. Two substances, carbon and oxygen, combine to form one substance, carbon dioxide. That's a combination reaction.
Okay.
Another fundamentally important one is the formation of water. Hydrogen gas, H2, combines with oxygen gas, O2, to produce liquid water, H2O. The balanced equation is 2H2G plus O2G, 2H2OL. Again, two elements combine to form a single compound.
Right. H2 and O2 making H2O all seem pretty straightforward.
They are, conceptually. Now, let's go back to that heat release we saw with quicklime. Remember activity 1.4, the beaker getting warm?
Yeah, it was exothermic.
Right. This leads us to a connected and very important concept for your exams, exothermic reactions. These are defined as reactions that release heat energy into the surroundings along with the formation of products. This release of energy typically causes the reaction mixture or its container to warm up.
So heat is a product. Kind of.
You can think of it that way, yes.
Right.
Heat is given off. And it turns out that all the combination reactions we just discussed, CaO plus H2O, C plus O2, H2 plus O2, are exothermic.
Okay. Are there other examples of exothermic reactions that aren't necessarily combination?
Absolutely. A very important one is the burning of natural gas, which is mostly methane, CH4. This is what many people use for cooking or heating. The reaction is CH4G plus 2OG plus 2H2OG plus energy. Lots of energy released as heat and light.
Right, that's definitely exothermic.
And here's a critical one, linking chemistry directly to biology. Respiration. The process our bodies use to get energy from food, is it exothermic or endothermic?
We get energy from it, so it must release energy.
Yeah.
Exothermic.
Exactly. Respiration is an exothermic process. We need energy to live, right? This energy comes from the food we eat. During digestion, complex carbohydrates like those in rice, potatoes, or bread are broken down into simpler sugars, primarily glucose, C6H12O6. This glucose then travels to our body's cells. Inside the cells, it reacts with the oxygen we breathe in. This reaction breaks down the glucose, releasing the vital energy required for all our life processes, moving, thinking, everything.
Wow. So breathing and eating power us through an exothermic reaction.
In essence, yes. The simplified overall equation for respiration is C6H12O6AQ plus 6O2AQ plus 6H2O2 plus 6H2O plus energy. Because energy is released, respiration is undeniably exothermic.
That's a really important connection.
It is. Even something like the decomposition of vegetable matter into compost, when leaves and food scraps break down in a compost heap. That process, carried out by microorganisms, also releases heat. It's exothermic.
Huh. I didn't know composting released heat.
It does. Now, one more practical application related to our slaked lime reaction, often asked in applied chemistry questions, is about whitewashing.
Using slaked lime for painting walls.
Exactly. A solution of slaked lime, calcium hydroxide, KOH2AQ, is applied to the walls. Over 2 to 3 days, this calcium hydroxide slowly reacts with the carbon dioxide, CO2, present in the air.
Reacts with the air.
Yes, and it forms a thin, hard layer of calcium carbonate, KCO3, on the walls. This calcium carbonate layer is what gives the whitewashed walls their characteristic shiny white finish. The reaction is KOH2AQ plus CO2G AKCO3 plus H2OL.
So the shine develops over time as it reacts with CO2.
Precisely. And an interesting fact, natural marble is also chemically calcium carbonate, KCO3.
Cool. Okay, quick question then. If so many combination reactions are exothermic, like the ones we saw, can we just say that all exothermic reactions must be combination reactions? Or is there a distinction we should remember, maybe for tricky multiple-choice questions in competitive exams?
That's an excellent question, and you've hit on a common point of confusion, exactly the kind of thing examiners like to test. While it's true that many combination reactions are indeed exothermic, because forming new, often stronger bonds releases energy, it is definitely not true that all exothermic reactions are combination reactions.
Okay, so they aren't the same thing.
Not at all. Think about respiration, which we just discussed. It's profoundly exothermic, right? It releases the energy we need to live. But is it a combination reaction?
Glucose and oxygen make CO2 and water.
Yeah.
It looks like things are breaking down more than combining.
Exactly. Respiration is a complex biological breakdown process. It involves multiple steps, but overall it's more like decomposition or combustion, certainly not a simple combination of two substances into one single product.
Right.
Similarly, remember the decomposition of vegetable matter into compost, we said that's exothermic too, but again, it's decomposition, things breaking down.
Okay, so exothermic just means heat is released regardless of how the atoms rearrange.
Precisely. Exothermic describes the energy change heat is released. Combination describes the structural change. 2 or more reactants form one product. They often overlap. Many combination reactions are exothermic, but they are not synonymous terms. That distinction is very important for conceptual clarity and avoiding traps in exams.
Got it. Exothermic combination always. Thanks.
You're welcome. Now let's smoothly transition to our next major type, which is essentially the opposite process, the decomposition reaction.
Opposite of combination. So one thing breaks into multiple things.
Exactly right. In a decomposition reaction, a single reactant breaks down or splits apart or decomposes to yield two or more simpler products. Think of it like taking apart a complex machine, like a clock, and getting back its individual gears and springs.
One compound, two or more simpler substances.
Perfect. Now, a key characteristic of decomposition reactions, and this is an important point for exams, they generally require an input of energy to happen.
Why do they need energy? Combination reactions often released energy.
Good thinking. Remember, reactions involve breaking old bonds and making new ones. In decomposition, you're primarily breaking the bonds holding the single reactant molecule together. Breaking bonds requires energy input. You have to supply energy maybe as heat, light, or electricity to overcome those bonds and make the compound split apart.
So you have to put energy in to break it down.
Exactly. This energy requirement makes most decomposition reactions endothermic unthermic. They absorb energy from their surroundings.
Opposite of exothermic. Endothermic needs energy.
Correct. And we can actually classify decomposition reactions based on the form of energy that's supplied to make them happen. This is often tested.
Okay, different energy types.
Yes. First, we have thermal decomposition, where the energy is supplied in the form of heat. Thermal relates to heat.
Breaking down using heat, like heating something strongly.
Precisely. Let's look at activity 1.5. Heating ferrous sulfate crystals. Ferrous sulfate crystals usually contain water molecules bound within their structure. We call this water of crystallization, and they typically have a pale green color. The formula is FeSO4.7H2O.
Okay, green crystals.
If you take about 2 grams of these crystals in a dry boiling tube and heat them gently over a flame, you'll observe 2 key things happening.
What should I look for?
First, the green color of the crystals will change. It usually turns whitish first as it loses water, and then often to a reddish-brown solid. Second, you'll likely detect a distinct pungent odor, which is characteristic of burning sulfur. Don't inhale it directly, just waft it carefully.
Okay, color change and a specific smell. What's actually happening chemically?
Good question. What happens is, first, the hydrated ferrous sulfate crystals, FeSO4.7H2O, lose their water of crystallization upon heating. They become anhydrous FeSO4.
They dry out.
Yes. Then, upon further strong heating, this anhydrous ferrous sulfate, FeSO4, decomposes. It breaks down into a solid product, which is ferric oxide, Fe2O3, that's the reddish-brown solid, and 2 gaseous products, sulfur dioxide, SO2, and sulfur trioxide, SO3. These gases are responsible for the pungent smell.
Wow, one thing made 3 things.
Exactly. The equation for the main decomposition part is 2 FeSO4s heat Fe2O3s plus SO2G plus SO3G. This clearly shows a single reactant FeSO4 breaking down into multiple simpler products, Fe2O3, SO2, SO3, driven by heat energy. Classic thermal decomposition.
Okay, that's a good example. Any others?
Yes. Another important one is activity 1.6. Heating lead nitrate powder. Lead nitrate, PbNO32, is a white crystalline solid.
Okay, white powder. What happens when you heat this one?
If you heat about 2 grams of lead nitrate powder strongly in a boiling tube held with tongs, you'll immediately observe the emission of distinct brown fumes. Very noticeable.
Brown fumes, what are those?
These characteristic brown fumes are nitrogen dioxide gas, NO2. The reaction that occurs is 2PbNO3 2 Hes, heat 2 PbOs plus 4NO2G plus OQG.
So the lead nitrate breaks down into lead oxide, PbO, a yellowish solid, the brown nitrogen dioxide gas, NO2, and also oxygen gas.
Perfectly described. Again, one reactant decomposes into 3 products upon heating, another clear thermal decomposition.
Are these just lab reactions or are there industrial uses?
Oh, absolutely crucial industrial applications. A prime example frequently asked about in application-based competitive questions is the thermal decomposition of calcium carbonate, CaCO3. Calcium carbonate is the main component of limestone.
Limestone, like the rock.
Exactly. When limestone is heated very strongly, say in a kiln, it decomposes. It breaks down to form calcium oxide, CaO, which we know as lime or quicklime, and carbon dioxide gas, CO2.
CaCO3 breaks into CaO and CO2.
Correct. The equation is KCO3 heat CaO plus CO2G. This reaction is absolutely fundamental in various industries. Quicklime, CaO, is a vital chemical base. The reaction is essential in the manufacture of cement, glass, and also for producing the quicklime itself. Huge industrial importance.
Wow. Okay, so thermal decomposition uses heat. What other energy types?
Right. The second type is electrolytic decomposition, where the decomposition is caused by passing electricity through a substance, usually when it's molten or dissolved in water. Electro refers to electricity. Lytic means breaking down.
Breaking down using electricity.
Exactly. The quintessential example here, a classic experiment, is activity 1.7, the electrolysis of water.
Passing electricity through water.
Yes. In the typical setup, you might use a plastic mug. You drill 2 holes at the base, fit rubber stoppers, and insert 2 carbon rods. These are your electrodes. I fill the mug with water, adding a few drops of dilute sulfuric acid. Why the acid?
Pure water doesn't conduct electricity well.
Exactly. The acid provides ions to help conduct the current. Then you invert 2 test tubes filled with water completely over the 2 carbon electrodes. Make sure no air bubbles are trapped inside.
Okay, test tubes over the electrodes.
Then you connect the electrodes to a power source, typically a 6-volt battery, and switch on the current. You leave it undisturbed for some time. What do you think you'll observe?
Electricity is passing through.
Decomposition.
Water should break down. Maybe bubbles forming.
Spot on. You'll observe bubbles of gas forming continuously at both electrodes. These bubbles rise and collect at the top of the inverted test tubes, displacing the water downwards.
So gas collects in both tubes. Is it the same gas? Same amount?
Excellent questions. You'll notice a critical difference. The volume of gas collected in one test tube is almost exactly double the amount collected in the other test tube.
Double the volume in one. Why?
Think about the formula for water, H2O. What's the ratio of hydrogen atoms to oxygen atoms?
2H for every 1O.
So?
2 to 1.
Exactly. And when water decomposes, it breaks down into hydrogen gas, H2, and oxygen gas, O2. The gas with double the volume is hydrogen, H2, and the one with the smaller volume is oxygen, O2. This directly reflects the 2.1 ratio in the water molecule.
Wow, the volume ratio matches the formula ratio.
It does, and you can even test the gases. If you carefully remove the test tube with more gas and bring a burning splint near its mouth, you'll hear a characteristic pop sound the test for hydrogen gas.
Pop sound for hydrogen. Okay.
If you test the gas in the other tube with less volume, with a glowing splint, not burning, just glowing red, the splint will burst back into flame, the test for oxygen gas.
Relights a glowing splint. Oxygen. Got it.
So the overall reaction is 2H2O electric current, 2H2G plus O2G. Here, electrical energy is the driving force breaking down water into its constituent elements. This experiment is fundamental. It shows decomposition by electricity and confirms the composition of water.
That's really neat. So we've had heat and electricity. What's the third energy source?
The third type is photolytic decomposition, where the decomposition is caused by light energy. Photo relates to light.
Breaking down using light. Like sunlight.
Exactly. Activity 1.8. Silver chloride in sunlight beautifully illustrates this. Silver chloride, AgCl, is a white solid.
Okay, another white powder.
If you take about 2 grams this white silver chloride powder in a clean china dish and simply place it out in direct sunlight for some time, you'll observe a gradual change.
What happens to it?
The white silver chloride slowly turns gray.
White to gray in sunlight. Why?
This color change happens because the light energy absorbed by the silver chloride causes it to decompose. It breaks down into metallic silver, Ag, which has a grayish appearance, and chlorine gas, Cl2, which escapes.
So light breaks AgCl into Ag and Cl2.
Precisely. The equation is 2AgCl, sunlight, 2Ag plus Cl2g. Silver bromide, AgBr, which is a pale yellow solid, behaves very similarly when exposed to sunlight. It also decomposes into silver metal and bromine gas. 2AgBrS, sunlight, plus Br2g.
Okay, so silver compounds broken down by light. Is this used anywhere?
Historically, yes. These photolytic decomposition reactions were absolutely foundational to traditional black and white photography. Photographic film used to be coated with emulsions containing silver bromide or silver chloride. When light hit the film, these compounds decomposed, forming tiny particles of silver metal, creating the latent image, which was then developed.
Wow, so old camera film used this chemistry.
It did indeed. So to quickly recap the decomposition types, thermal, heat, electrolytic, electricity, and photolytic, light. What did we say was common to all of them in terms of energy?
They all require energy input to break the reactant down.
Exactly. They need energy to proceed. This brings us back nicely to our connected concept, endothermic reactions. Remember what endothermic means.
Heat or energy is absorbed from the surroundings, the opposite of exothermic.
Perfect. Reactions in which energy is absorbed are known as endothermic reactions. And all these decomposition reactions we just discussed, heating ferrous sulfate, heating lead nitrate, electrolysis of water, silver chloride, and sunlight, are prime examples of endothermic processes because they require a continuous supply of energy, heat, electricity, or light from the surroundings to occur.
So decomposition reactions are generally endothermic.
Generally, yes. Another common classroom demonstration of an endothermic reaction is mixing solid barium hydroxide with solid ammonium chloride in a test tube. If you do this and touch the bottom of the test tube, it feels distinctly cold.
Cold, why?
Because the reaction between them absorbs heat energy from the surroundings, including the glass tube in your hand, making it feel cold. That's a direct physical sensation of an endothermic process.
It seems really crucial to identify the energy source for decomposition reactions, like thermal, electrolytic, or photolytic. Is that a common question type in competitive exams, maybe asking us to give examples or identify the type from a description?
Absolutely, that's a very common type of question, especially in multiple choice formats for competitive exams like NEET or G, and even in board exams, you will often be asked to 1. Identify the specific type of decomposition, thermal, electrolytic, photolytic, based on the energy source mentioned or implied in the reaction conditions. For example, seeing heat or is over the arrow, electric current, or sunlight high. 2. Provide an example reaction for each type of energy input. 3. Explain why energy is needed for decomposition, which is fundamentally to break the existing chemical bonds within the reactant molecule. So yes, understanding not just that decomposition happens, but how which energy source drives it is crucial for both conceptual clarity and for scoring well on those specific question types. Make sure you know at least one key example for each.
Okay, we'll definitely focus on knowing the examples and the energy types for decomposition.
Good plan. Now, let's move on to the third major type of chemical reaction we need to cover. Displacement reactions.
Displacement. Sounds like something is getting pushed out of place.
That's exactly the idea. In a displacement reaction, a more reactive element displaces or removes or kicks out another less reactive element from its compound. This typically happens when the compound is dissolved in a solution.
More reactive pushes out less reactive, like a stronger person taking a seat from someone weaker.
That's a pretty good analogy, actually. The strength here is chemical reactivity. Let's look at the classic, highly illustrative example, activity 1.9, iron nails dipped in copper sulfate solution.
Okay, iron and copper sulfate. What's the setup?
You typically take 3 iron nails. It's important to clean them first, usually with sandpaper. Why clean them?
To remove any rust or oxide layer so the pure iron reacts.
Exactly. Then you take 2 test tubes, maybe label them A and B. In each, you put about 10 millimeters of copper sulfate solution. What color is copper sulfate solution usually?
It's blue, right? A distinct blue color.
Correct. Now, you tie 2 of the cleaned iron nails together with a thread and carefully immerse them in the copper sulfate solution in test tube B. You leave them undisturbed for about 20 minutes. The third iron nail and test tube A, which just contains the original copper sulfate solution, are kept aside for comparison later.
Okay, nails soaking in blue solution for 20 minutes. What do we expect to see?
After about 20 minutes, when you carefully take the iron nails out of the solution in test tube B, you'll observe a very clear change. Compare them to the nail you kept aside.
How do they look different?
The iron nails that were dipped in the copper sulfate solution, which were initially shiny and grayish, will now have a distinct brownish coating on their surface.
Brown coating on the iron. What's that?
That brownish coating is actually metallic copper that has been deposited onto the surface of the iron nails.
So copper came out of the solution onto the nail.
Precisely. And that's not the only change. Look at the solution in test tube B and compare it to the original blue solution in test tube A. What do you notice about the color?
If copper came out of the solution, the blue color should fade.
Exactly. The distinct blue color of the copper sulfate solution in test tube B will have faded significantly. Often it turns into a pale green color.
Blue fades, turns greenish, and brown stuff appears in the nail. What's the chemical explanation?
The reaction happening is FeS plus SO4AQ, Fe4AQ plus QS.
Iron plus copper sulfate yields iron sulfate plus copper.
Perfect. In this reaction, iron Fe has displaced or removed the copper C from the copper sulfate CuSO4 solution. The pale green solution that forms is iron 2 sulfate, PiSO4. The solid brown coating is the displaced copper metal, CuS.
So iron basically kicked copper out of its compound.
Yes, and why could iron do that? It happens because iron is more reactive than copper. The more reactive iron effectively pushes out, the less reactive copper from its compound and takes its place in the solution. This entire process, a more reactive element displacing a less reactive one from its compound, is a displacement reaction.
Okay, that makes sense. Iron, copper, and reactivity. Are there other examples?
Absolutely. Think about using zinc metal instead of iron. Zinc is also more reactive than copper. So if you put zinc granules in copper sulfate solution, ZnS plus CuSO4AQ plus QS,
Zinc displaces copper too. What would we see?
you'd see the blue color fade, maybe become colorless since zinc sulfate is colorless, and you'd see reddish-brown copper metal depositing on the zinc.
Okay, what about lead?
Lead is also more reactive than copper. So if you put lead metal in, say, copper chloride solution, which is also usually blue or green, PbS plus KCl2AQ, PbCl2 plus QS, lead displaces copper, forming lead chloride solution and copper metal.
So the key seems to be knowing which metal is more reactive.
You've nailed it. The underlying principle behind all these examples is the reactivity series of metals. This is a list that ranks metals, and sometimes nonmetals like hydrogen, in order of their decreasing reactivity.
A ranking from most reactive to least reactive.
Exactly. Elements higher up in the series are more reactive. They have a greater tendency to lose electrons and form positive ions. Because of this greater tendency, they are able to displace elements that are lower down, less reactive, from their compounds in solution.
So knowing this series helps predict if a reaction will happen.
Absolutely crucial. Understanding the reactivity series is essential for predicting the outcome of displacement reactions in your exams. You'll often get questions asking, will reaction occur between metal X and solution Y? You need to compare their positions in the series to answer correctly.
So understand the reactivity series is absolutely key for predicting displacement reactions. Do we need to, memorize the entire series for the exams, or is it more about understanding the concept?
That's a very practical question. For most board exams and competitive exams at this level, like Class 10, Foundation Nietzsche, while knowing the full reactivity series in detail can certainly be beneficial, the main emphasis is usually on understanding the concept and being familiar with the relative reactivity of the most commonly encountered metals.
Which ones are most common?
You should definitely focus on knowing the relative order of metals like potassium K, sodium No, calcium K, magnesium Mg, aluminum Al, zinc Zn, iron Fe, lead Pb. Then often hydrogen H is included as a crucial reference point, especially for reactions with acids. And then below hydrogen come copper, C, silver H, gold Au, and platinum Pt.
So K, K are very reactive. ZO, Phe, Pb are in the middle. Q, Ag, U are less reactive.
That's the general idea. You won't typically be asked to just recite the entire series from memory. Instead, you'll need to apply the principle to specific reaction scenarios given in the question. The essential takeaway, the core concept is, a metal higher in the series can displace a metal lower in the series from its compound solution. Knowing the relative positions of common metals like zinc, iron, lead, copper, silver is usually sufficient to tackle most problems.
Okay, focus on the common ones and the principle. That seems manageable.
Right. Now let's discuss the fourth major type of reaction. Double displacement reaction.
Double displacement. Sounds like two things are getting displaced.
In a way, yes, but it's more like an exchange. These reactions differ significantly from single displacement. There isn't just one element replacing another. Instead, in a double displacement reaction, there's an exchange of ions between the two reacting compounds.
Exchange of ions. How does that work?
Think of two ionic compounds in solution, say AB and CD. Compound AB consists of A ions and BA ions. Compound CD consists of C ions and D ions. In a double displacement reaction, they essentially swap partners. The A ion combines with the D ion, and the 2 ion combines with the Ba ion, forming two new compounds, AD and CB.
Like switching partners in a dance. A dances with D, C dances with B.
That's a perfect analogy. It's exactly like two pairs of dancers swapping partners to form two new pairs. It's an exchange between the positive ions and the negative ions of the reactants.
Okay, ion exchange. Does anything special often happen in these reactions?
Yes, very often. A very significant subset or outcome of double displacement reactions are what we call precipitation reactions.
Precipitation, like rain.
Hey, related root word, but in chemistry, it means something different. Remember way back in activity 1.2, when we mixed lead nitrate and potassium iodide, and we saw that insoluble white substance form instantly.
Oh, right, the solid appearing from liquids. You called it a precipitate then, too.
Exactly. Many double displacement reactions result in the formation of one of the new products, like AD or CB in our analogy, being insoluble in the solvent, usually water. This insoluble substance that forms and usually settles out of the solution is called a precipitate. Any reaction that produces such an insoluble solid is specifically termed a precipitation reaction. These are extremely common, especially in qualitative analysis in chemistry labs, to identify ions.
So double displacement often leads to a precipitate forming.
Very often, yes. Let's illustrate this clearly with activity 1.0, mixing sodium sulfate and barium chloride solutions. Both of these are typically available as clear, colorless aqueous solutions.
Okay, two clear solutions again. What happens when we mix them?
If you take about 3 millirel of sodium sulfate solution, Na2SO4, in one test tube, and about 3 milliliters of barium chloride solution, BaCl2, in another, and then simply pour one into the other, you'll immediately observe the formation of a white substance that is insoluble in water. It makes the mixture look cloudy or milky, and eventually, this white solid will settle down if left undisturbed.
Instant white solid again. That's the precipitate.
That's the precipitate. In this specific reaction, the white precipitate formed is barium sulfate. Barium sulfate. Why did that form?
Let's think about the ions. Sodium sulfate solution contains NiO ions and SO4 ions. Barium chloride solution contains baryonions and Cli ions. When you mix them, the ions swap partners according to our double displacement model.
So NiO goes with Cli and baro goes with SO.
Exactly. The sodium ions, NiO, combine with the chloride ions, Scl, to form sodium chloride, NaCl. Is sodium chloride soluble in water?
Yeah, table salt dissolves easily, so NaCl stays dissolved. Right, it remains in the aqueous solution, AQ. But the other pair, the barium ions, combine with the sulfate ions, SOO, to form barium sulfate, BaSO4. And it turns out that barium sulfate is insoluble in water. Because it's insoluble, it forms as a solid precipitate.
So the insolubility of BaSO4 is why we see the precipitate.
Precisely. The overall equation for this double displacement reaction is Na2SO4AQ plus BaSO2SO plus 2 NaClS. You can clearly see the exchange of ions and the formation of the solid precipitate BaSO4.
Okay, that makes the ion exchange and precipitation clear.
Good. And just to tie it back one more time to an earlier observation, remember activity 1.2, the reaction between lead-2 nitrate solution, PbNO32AQ, and potassium iodide solution, KiAQ.
Yeah, that one made a precipitate too, but I think you said white then. Or was it different?
Ah, good memory. But let's refine that observation. The precipitate formed in the lead nitrate and potassium iodide reaction is actually a distinct yellow color.
Yellow precipitate. Okay, what is it?
That vibrant yellow precipitate is indeed lead iodide, PbI2. Its formation is also a result of a double displacement reaction.
So PbO ions from lead nitrate swap with cations from potassium iodide.
Let's be precise with the ion swap. The positive ion from one, PbO, combines with the negative ion from the other, and the other positive ion combines with the other negative ion.
Ah, okay. PbO with IO makes PbI2, and Co with no A makes KNO3.
Exactly. And lead-2 iodide, PbI2, happens to be insoluble in water, forming the yellow precipitate. Potassium nitrate, KNO3, is soluble, so it stays in solution. The equation is PbNO3 2AQ plus 2Ki, AbI2, plus 2KNO3AQ. This beautifully confirms it as another double displacement reaction where ions are exchanged, leading to an insoluble precipitate. Understanding these patterns of ion exchange and knowing some common solubility rules, which you'll learn more about later, is vital for predicting products in competitive exams.
Okay, double displacement means ion exchange, often forming a precipitate if one product is insoluble.
Got it. Excellent. Now, we arrive at a pair of absolutely crucial chemical processes. These are fundamental to understanding a vast range of reactions, including many we've already touched upon, plus processes in everyday life, complex biological systems, and industrial chemistry. We're talking about oxidation and reduction.
Oxidation and reduction. I've heard these terms a lot. Aren't they opposites?
They are indeed opposites, but they are also intrinsically linked. You almost never have one without the other. They always occur simultaneously in reactions, forming what we collectively call redox reactions, reduction oxidation.
Redox, okay. How are they defined?
Let's start with an activity to illustrate the concepts visually. Consider activity 1.11. Heating copper powder. Copper metal, as you know, has a characteristic reddish-brown color.
Like copper wires.
If you take about 1 gram of this copper powder in a clean china dish and heat it strongly in the air, maybe over a Bunsen burner, you'll observe a distinct change on the surface.
What happens to the copper?
The surface of the reddish-brown copper powder becomes coated with a black substance.
Copper turns black when heated in air. Why?
Good question. This happens because oxygen from the surrounding air reacts with the hot copper. The black substance formed is copper-2 oxide, CuO.
So copper plus oxygen makes copper oxide, like a combination reaction.
It is a combination reaction, yes, but we can also look at it in terms of oxygen gain. Copper, C, has gained oxygen to become copper-2 oxide, CuO. This process, where a substance gains oxygen during a reaction, is one definition of oxidation.
Gain of oxygen, oxidation. So copper got oxidized here.
Precisely. The equation is 2CuS plus O2G heat 2CuO. Copper is oxidized.
Okay, that's oxidation. What about reduction?
Now let's consider the reverse scenario. Suppose we take this black copper oxide, CuO, that we just formed, keep it hot, and pass hydrogen gas, H2, over it.
Hydrogen gas over hot black copper oxide. What happens then?
Something interesting happens. The black coating on the surface turns brown again, and you might observe some tiny droplets of water forming, perhaps condensing on cooler parts of the apparatus.
Black turns back to brown. That means copper metal is forming again.
Exactly. The copper metal C is being reformed. Let's look at the equation for this reverse reaction. CuOS plus H2G heat HUS plus H2OG.
Okay, CuO plus H2 makes Q plus H2O.
Now, analyze what's happening in terms of oxygen. What is happening to the copper-2 oxide, CuO?
CuO is turning into Q. It's losing its oxygen.
Correct. When a substance loses oxygen during a reaction, it is said to be reduced. So in this reaction, copper-2 oxide is being reduced to copper.
Loss of oxygen reduction, CuO is reduced.
Right, but look carefully at the same reaction. What's happening to the hydrogen gas, H2?
H2 is turning into H2O. It's gaining oxygen.
Exactly. And what do we call the process of gaining oxygen?
Oxidation. So hydrogen is getting oxidized.
Perfect. So look at this single reaction, CuO plus H2Q plus H2O. In the same reaction, one substance, copper oxide, is getting reduced, losing oxygen, while simultaneously another substance, hydrogen, is getting oxidized, getting oxygen.
Wow, reduction and oxidation happening together in the same reaction.
Precisely, and that's the key point. Reactions where oxidation and reduction occur simultaneously are called oxidation-reduction reactions, or much more commonly, redox reactions. You can't have one without the other. If something loses oxygen, is reduced, something else must be gaining it, is oxidized.
Okay, redox means both happen together. Are there other ways to define oxidation and reduction beside oxygen gain loss?
Yes, there are, and these broader definitions become more important as you study more chemistry, especially when reactions don't involve oxygen. We can also define them in terms of hydrogen transfer, or most generally, in terms of electron transfer. Let's solidify the common definitions you need at this stage. Oxidation is defined as the gain of oxygen by a substance, or the loss of hydrogen by a substance during a reaction. For later, it's also the loss of electrons. Reduction is defined as the loss of oxygen by a substance, or the gain of hydrogen by a substance during a reaction.
For later, it's also the gain of electrons.
Gain O, lose H equals oxidation. Lose O, gain H, reduction. Okay, those are the key pairs. Exactly, memorize those pairs. They are crucial because, as we saw, oxidation and reduction always occur in tandem in a redox reaction. One substance acts as the oxidizing agent. It causes oxidation by getting reduced itself, and the other acts as the reducing agent. It causes reduction by getting oxidized itself.
Oxidizing agent gets reduced, reducing agent gets oxidized. A bit confusing.
It can seem that way at first.
Yeah.
Just remember, the agent does the opposite to itself. The oxidizing agent causes oxidation, takes electrons, gives oxygen, takes hydrogen from something else, so it itself gets reduced. The reducing agent causes reduction, gives electrons, gives hydrogen to something else, so it itself gets oxidized.
Okay, I'll need to review that agent part carefully.
Let's look at a couple more examples of redox reactions using our definitions. Consider the reaction ZNOS plus CNS plus COG. What's happening to carbon C?
C is becoming Ca. It's gaining oxygen, so carbon is oxidized.
Perfect. And what's happening to zinc oxide, ZNO?
ZO is becoming Zn. It's losing oxygen, so zinc oxide is reduced.
Excellent. So it's a redox reaction. Carbon is oxidized, ZNO is reduced, which is the oxidizing agent.
One that gets reduced. So ZNO is the oxidizing agent.
And the reducing agent.
One that gets oxidized, so carbon is the reducing agent.
You've got it. See? Once you break it down, it makes sense. One more. MnO2 plus 4HCl MnCl2 plus 2H2Ol plus Cl2G. This one's a bit more complex. Let's look at hydrogen chloride, HCl. It becomes chlorine Cl2, among
Yeah.
other things. What has HCl
And
lost?
HCl to Cl2. It's
Yeah.
lots of hydrogen.
Yeah.
Lots of hydrogen. That's oxidation. So HCl is oxidized.
Very good. Now look at manganese dioxide, MnO2. It becomes manganese chloride, MnCl2. What has MnO2 lost?
MnO2 to MnCl2. It's lost its oxygen.
Yeah.
Loss of oxygen. That's reduction. So MnO2 is reduced.
Fantastic. So again, it's a redox reaction. HCl is oxidized, acting as the reducing agent, and MnO2 is reduced, acting as the oxidizing agent.
Okay, looking for oxygen or hydrogen gain loss helps identify redox.
Exactly. And just to connect back quickly to an earlier activity, remember activity 1.1, the magnesium ribbon burning in air, Mg plus O2 AMGO. What happened to the magnesium?
Magnesium gained oxygen to form MgO. So magnesium was oxidized.
Perfect. Understanding these redox concepts helps you analyze and classify a huge number of chemical reactions. For competitive exams, being able to confidently identify which reactant is oxidized, which is reduced, and which substance is the oxidizing agent versus the reducing agent is a very frequently tested skill.
Right. Definitely need to practice identifying those roles.
Okay, finally, let's wrap up by discussing some real-world implications of these oxidation reactions. These are things you encounter literally every single day, and they often form the basis for application-based questions in your exams, highlighting why understanding this chemistry is practically important.
Okay, everyday oxidation effects.
Yes, two significant ones we need to cover: corrosion and rancidity. First, let's talk about corrosion. You must have observed that new iron articles, think of gates, railings, car bodies, tools, they're shiny when new, right?
Yeah, usually silvery or gray and shiny.
But what happens if they are left exposed to the atmosphere, especially if it's humid or rainy for some time?
They get that reddish-brown, flaky stuff on them. Rust.
Exactly. That process is what we commonly know as the rusting of iron. Rusting is a specific example of the broader phenomenon called corrosion.
So corrosion is the general term, and rusting is corrosion of iron.
Precisely. Corrosion is defined more generally as the process by which a metal is gradually degraded or eaten away by reacting with substances in its environment, primarily moisture, water, oxygen from the air, acids, salts, or other atmospheric gases. When this attack happens, the metal is said to corrode.
Are there other examples besides iron rusting?
Oh, yes. Think about silver articles, like jewelry or silverware. They're bright and shiny when new, but over time, they often develop a black coating. That's corrosion too, silver reacting with traces of sulfur compounds in the air to form black silver sulfide.
Ah, the tarnish on silver, that's corrosion.
It is. Another example is copper. Copper objects like roofs or statues or even old pennies often develop a characteristic green coating over time, especially outdoors. This green layer is usually basic copper carbonate formed by copper reacting with oxygen, carbon dioxide, and moisture in the air. That's also corrosion.
Okay, rusting iron, tarnishing silver, green copper, all corrosion. Why is it such a big deal?
The impact of corrosion, particularly the rusting of iron, is absolutely immense economically and structurally. It causes significant damage to critical infrastructure. Think about car bodies weakening, bridges becoming unsafe, iron railings crumbling, ships deteriorating. Rusting is a very serious global problem. It costs enormous amounts of money, billions worldwide, every single year just for replacing corroded iron and steel structures and for implementing prevention methods.
Wow, billions just because of rust.
It's a huge issue. You'll actually delve into more details about the specific electrochemical mechanism of rusting and various sophisticated prevention methods like galvanization, coating iron with zinc, electroplating, using alloys, painting, oiling in Chapter 3, which focuses more on metals and nonmetals. But the basic idea is that it's an undesirable oxidation process.
Okay, so we often paint iron gates or railings at home. You mentioned painting as a prevention method. Is painting essentially a way to stop this corrosion, and how does it specifically relate to preventing the oxidation part?
That's a keen observation and an excellent practical application. Yes, painting iron articles is indeed one of the most common, relatively inexpensive, and often effective methods used to prevent rusting, which, as we said, is a specific form of corrosion.
How does the paint actually stop the rust?
In terms of preventing oxidation, here's the simple but effective mechanism. The paint acts as a physical barrier. It creates a continuous protective layer or coating over the surface of the iron.
A barrier between the iron and the air.
Exactly. This barrier completely prevents the surface of the iron metal from coming into direct contact with the two key ingredients required for rusting to occur: oxygen from the air and moisture, water, humidity. By creating this physical separation, the paint effectively cuts off the iron's access to the oxidizing agents, oxygen and water. If the iron can't interact with oxygen and water, the oxidation process that leads to rust simply cannot start or is greatly slowed down. So, painting inhibits corrosion primarily by preventing the oxidation of the iron.
Simple barrier, big effect. Makes sense.
It does. Now, the second significant effect of oxidation in everyday life we need to discuss is rancidity.
Rancidity sounds unpleasant, like food going bad.
Exactly like food going bad, specifically food that contains fats or oils. Have you ever tasted or smelled, say, old potato chips, nuts, or maybe cooking oil that has been sitting around for a very long time, especially if it wasn't stored properly or it's been warm?
Yeah, they get that stale sort of off smell and taste.
Yeah.
Not nice.
That unpleasant spoilage, that change in smell and taste, is precisely what we call rancidity. It occurs when the fats and oils present in the food materials undergo oxidation by reacting with the oxygen present in the air.
So oxygen attacks the fats and oils.
Yes. This oxidation process leads to the chemical breakdown of the fats and oils into other compounds, often volatile aldehydes and ketones, which have those characteristic undesirable rancid smells and tastes. This is why fatty foods don't stay fresh forever.
Okay, so rancidity is fate oil oxidation. Can we prevent it?
Fortunately, yes. There are several crucial methods used to prevent or at least significantly slow down rancidity. These are vital for food preservation and are frequently asked about in your exams, often in application-based questions.
What are the methods?
One common method is by adding antioxidants to foods that contain fats or oils.
Antioxidants, I've heard of those, like in vitamins.
Yes, some vitamins like C and E are antioxidants, and others like BHA and BHT are often added commercially. Antioxidants are substances that prevent oxidation. They work by being more easily oxidized themselves than the fats or oils. They essentially sacrifice themselves, reacting with the oxygen before the fats and oils get a chance to, thus protecting the food and preserving its freshness.
So they take the hit instead of the fat? Clever.
It is. Another very simple yet effective method is keeping food in airtight containers. Why would that help?
Airtight. Less air means less oxygen can get to the food.
Exactly. By minimizing the exposure of the food to atmospheric oxygen, you significantly slow down the rate of the oxidation process that causes rancidity. Simple physics, effective chemistry.
Okay, airtight storage. What else?
Perhaps the most commercially visible example you encounter almost every day, especially if you eat packaged snacks, relates to bags of chips or similar products. Have you noticed they often seem quite puffy, filled with gas?
Yeah, chips bags are mostly air. Or gas, anyway.
Right, but it's usually not just regular air. Chips manufacturers typically flush the bags with an inert gas, most commonly nitrogen, before sealing them.
Flushing with nitrogen. Why nitrogen instead of air?
Air, as we know, contains about 21% oxygen, which is reactive and would cause the fats and oils in the chips to go rancid quickly. Nitrogen gas, N2 on the other hand, makes up about 78% of air, but is extremely inert or unreactive under normal conditions. It does not readily react with the fats and oils.
So the nitrogen creates a protective atmosphere without oxygen.
Precisely. By replacing the oxygen-rich air with inert nitrogen, they prevent the chips from getting oxidized. This preserves their crispness, taste, and freshness for a much longer shelf life. It's a brilliant, large-scale application of preventing unwanted oxidation in the food industry.
Wow, that's why they do that. Very practical chemistry.
It is indeed. So those are the key everyday effects, corrosion and rancidity, both essentially undesirable oxidation processes.
All right, so we've covered a vast, and I hope you agree, incredibly important ground today in our deep dive into chemical reactions and equations. Let's just do a quick recap of the core learning points. These are absolutely essential for you to take away for your upcoming board exams and those competitive exams like NEET, JG, UPSC, SSC, and state PSCs.
Okay, so quick summary would be great.
Right. We started by understanding how to identify that a chemical reaction has actually happened. What were those 4 key observable changes?
Change in state, change in color, evolution of a gas, and change in temperature.
Excellent. Those are your fundamental cues, especially in a lab setting. Then we moved on to how we represent these reactions using the language of chemistry. We started with descriptive word equations, but quickly saw the need for precise chemical equations using chemical formulae.
Like Mg plus O2 MgO.
Exactly. And we stressed the absolute importance of the law of conservation of mass. Why does this law mean equations must be balanced? Because atoms can't be created or destroyed, so the number of each type of atom must be the same on both sides of the equation.
Perfect. We walked through the systematic hit and trial method for balancing, ensuring those atom counts are identical. We also covered the importance of making equations even more informative by including physical state symbols, S, L, G, and especially AQ for aqueous solutions, and sometimes indicating reaction conditions like temperature, pressure, or catalysts above or below the arrow.
Right, getting the full picture.
Then the major part was classifying reactions into 4 main types based on how atoms rearrange. What was the first type?
Combination reaction.
Sure.
2 or more substances form a single product, like Caryo plus H2O, KOH2.
Good, and these are often.
Often exothermic, releasing heat.
Great. What was the opposite of combination?
Decomposition reaction. A single substance breaks down into 2 or more simpler products, like KCO3, HEOO plus CO2.
And what do these usually require?
They require energy input, heat, thermal, electricity, electrolytic, or light, photolytic. So they're usually endothermic.
Fantastic recall. What was the third type?
Displacement reaction.
Yeah.
A more reactive element kicks out a less reactive element from its compound, like Phe plus QSO4 or FeSO4 plus Ke. Depends on the reactivity series.
Excellent. The reactivity series is key there. And the fourth type?
Betel displacement reaction. An exchange of ions between 2 compounds, like Na2SO4 plus BasoBiso plus 2N-asciol. These often form an insoluble solid, a precipitate.
Perfect summary of the 4 main types. Then we dug into redox. What are the core definitions of oxidation and reduction we focused on?
Oxidation is gain of oxygen or loss of hydrogen. Reduction is loss of oxygen or gain of hydrogen.
Good. And they always happen together and...
Redox reactions.
Exactly. Where one substance gets oxidized and the other gets reduced. And finally, to round it all off, we discussed those tangible effects of oxidation in everyday life. What were the 2 main examples?
Corrosion, like the rusting of iron, which causes damage. And rancidity, the spoilage of fats and oils in food due to oxidation.
And we talked about prevention methods like painting for corrosion and using antioxidants, airtight containers, or nitrogen flushing for rancidity.
Right.
Okay, that covers the main points. Now, my dear students, listen carefully. This chapter truly forms the bedrock of your inorganic chemistry understanding. To really master it, ensure you revise all these concepts thoroughly. Definitions, examples, the works.
Okay.
Make absolutely sure you practice writing and balancing chemical equations for all the reaction types we discussed today. I guarantee you this is a skill that will be tested often multiple times in your board exams and in your competitive papers. Don't skip the practice.
Will do. Practice balancing.
Yes. Also, attempt all the exercises at the end of this chapter in your textbook. And very importantly, try to find and solve past year questions related to this chapter from your specific exam, board, NEET, JG, etc. See how these concepts are actually framed in exam questions.
Fast papers are key, yes.
They really are. If you face any specific challenges while studying, maybe a particular type of balancing problem, or you have further doubts about any concept we covered, please don't hesitate to reach out. Ask your teachers, ask your tutors, discuss with friends. Don't let doubts linger. Keep practicing consistently, put in the hard work, and success will definitely be yours.
Thank you so much for this clear and really detailed deep dive, breaking down the balancing step by step and connecting the types to activities in everyday life, plus those exam insights. It really makes this chapter click much better now. I'll definitely make sure to put in the practice and solidify these concepts before moving on.